Hello everyone, we're going to have a look at an example involving the probability density function for a continuous random variable. So here's the question written here. Okay, that's what we're looking at. So we're going to consider the exponential probability density function for this rule here. Okay, now this is in two pieces. So this is what happens when x is bigger than 0 here, and this is what happens when x is less than or equal to 0. So the first thing is to sketch the graph. So in order to sketch the graph, look down here. I'm going to say that to sketch the graph, note that when x is greater than 0, the graph is the exponential graph of 2e to the minus 2x, that one there. Okay, so over here, this bit here is the graph when x is greater than 0. Okay, because that's where this is the x-axis along here, and this is where x is greater than 0 in that direction. And that's what's happening there. Okay, so what happens when the graph is, when x is less than 0? Y just equals 0. So all the way across here, because that's where x is less than or equal to 0, we just got it across the line, y equals 0. Now, there's one extra little bit to notice here. It's these open dots and closed dots. So what that is where x is greater than 0, that's this one here, where x is greater than 0 in that way, we are not including this bit, not including it, when only greater than. And that open dot means not including it. Where x is less than 0, we are including it. That's why the dot is coloured in. And then the graph is those two pieces put together. Okay, part A. Now we're going to go to part B. Show that the graph is a probability density function. Okay, so to be a probability density function, this comes straight out of the definitions. Here it is. It's got to satisfy the two things. All the values have to be greater than 0 for all values of x, the value of the function. And the area under the curve from minus infinity to infinity has to equal 1. So let's have a look at this. So the first point number 1 here, we can see on the graph that all the values are greater than or equal to 0. They're all either on the x-axis or above the x-axis. Okay, everything is above the x-axis or on it. Therefore, it meets the first requirement that the function is always equal to 0 or above 0. The second thing is to check that the integral under the curve from minus infinity to infinity is 1. So we need to set up the function. Now, we don't need to worry about doing the area under the curve from here onwards, because that is going to be 0. There's no area under the curve. What we're interested in is this bit here, all the way up there. So when we set up the function, when we set up the integral, that's going from minus infinity to infinity. Immediately we can start from 0 rather than worrying about minus infinity, because we didn't have to go that far. Now, the problem is when you are going to integrate and you've got an undefined endpoint like the infinity, you're going to have to use limits. So what we need to do is we set a limit as k approaches infinity from 0 to k, from there to there, and then you do the actual function, find the integral of the function. So let's have a look at that. When you integrate 2e to the minus 2x, remember, with integration of exponentials, you write the exponential bit exactly the same. Okay, so that's what you have to do there. So let's have a look here. Have we got the integrant into the exponential bit exactly the same? Yep, there it is. Okay, and then you also need the constant out the front. So what you do need to do, though, is when you've written that bit exactly the same, so the e to the minus 2x bit exactly the same, when you're integrating, you need to divide by the derivative of the power. So the derivative of the power is minus 2. So you'd need to divide by that minus 2. When you look over here at the what the work was done here from the textbook, it has divided by that minus 2. Okay, so our limits are going from 0 up to k, and k is as approaches infinity. So let's substitute what we can, or they simplify first, sorry. 2 goes into 2, that simplifies, we've got the minus e to the minus 2x. So let's substitute in. The k goes in, e to the minus e to the minus 2k. That's substituting the k. Then we substitute in the 0, minus e to the minus 0. Now we can actually work that out. Now this bit here is pretty easy because anything to the power of 0 is 1. So it doesn't matter what it is. Anything to the power of 0 gives you 1. So all of that to the power of 0 is just going to be 1. So that's shown over there. That would equal 1. So it's the other bit that's the interesting bit. What's happening here? What we have to do is worry about what is happening to this function as k is getting bigger and bigger and bigger. And probably the easiest way to do that is to have a look at the graph of it. So here is the graph of minus e to the minus 2x. See, it's the same as that bit there. So we can do that. What's happening to it? As x is getting bigger and bigger and bigger, tending towards infinity, okay, as it heads off there towards infinity, what's happening to the graph? Well, it starts down here, but it's getting closer and closer and closer to 0. And as you can see, the graph is tending towards 0. So that's why they put a 0 there. So we know that this is 1, and we know that's 0. 1 plus 0 gives you 1. So, yep, it satisfies the two conditions for the probability density function. Okay, remember those two conditions back up here. Okay, that was question B. Show that it's a probability density function. Question C, up here now we want to do, find the probability of x is greater than 1. X is greater than 1. Okay, so let's go down and do this. It's another integration question. Okay, here we go, x is greater than 1. Again, we're going to, there's no limit to the top, or the limit is infinity, it goes on forever, so we have to do, put in the limit notation there. But the bottom, this time, rather than starting from 0, we're starting at x needs to be bigger than 1, so we can put a 1 on the bottom. So this is pretty much the same as the previous question, except for when we do our integration, we're substituting in from 1 up to k. So we put 1 in here rather than 0, and we put in k in here just like we did before. Now, just like we did before, this whole thing is going to tend towards 0. That's why I get there. And the second bit is a, you're not going to get a nice number. You just can leave it in terms of e. And so then that's 0 plus whatever that is in terms of e. That's an exact answer, and that's to 4 decimal places. And you're done.